Hi grade 11s, we're on to topic 3.8, which is our last type of reduction. This is reduction when you're working with 90 degrees. Now you'll notice that all the other reductions we kind of kept together as one family, and this is, almost entirely on its own. And I will show you why, because it's almost like an entirely different thought process. So what I've set up here is I've set up an axis with an angle of theta, and let us pretend that these land up at a point, let's call it point P, and we're going to call it coordinates AB. And then the R value we're just going to call R. So that means immediately I can write down what cos, sine, and tan are of theta. Okay, so I've written down what the kind of values or would be of sine, cos, and tan, but basically I just use the letters. So the definition of sine is y over r, so it's in this case with my letters it would be over r, and then cos would be a over r, and tan would be b over a. Now what we're trying to create is, when I say reductions from 90, the one we're going to look at in this video is how do I create an angle of 90 degrees minus theta, and then how do I make an angle of 90 degrees plus theta, because so far we've only dealt with creating reductions that work from 180 and from 360 degrees. Okay, so what I'm going to do here is, how do I construct an angle of 90 minus theta? Well, the first thing that I would do is I would draw a line which goes straight through the middle of my Cartesian plane, and this would be the line y is equal to x. Now what we're going to do is we're going to reflect this arm, this r that we have so far that's causing a value of theta. We're going to reflect that over this line y is equal to x. So literally it's almost like drawing this on your page and then folding your page along my y is equal to x along my blue line. Now what would happen then is that r, that arm that I created theta with, would land up there. Now that doesn't look particularly symmetrical, so let me try to draw it a little bit better. So if I try and draw it a little bit more accurately, basically I'm folding it over. So this angle here should be approximately the same as that. If you do it accurately, it should be identical, because I'm busy folding it over. Now if this is exactly folded over, the symmetry that is created is that this angle there would now be theta. So almost try and tilt your head on the side, so kind of move your page a bit and look directly at this line of y is equal to x and see that this is a mirror image onto that side. Okay, now by doing this reflection, what have I created? I've created an angle. Remember, we always measure angles from the x-axis anti-clockwise to the line. So what is that angle there? Well, if it's theta from the 90 degrees, this angle here that I've now created is 90 degrees minus theta. So now I can start talking about sine of that angle and cos of 90 minus theta and tan of 90 minus theta. The question is, what happened to P if I reflected it over? So this point over here, I'm going to call it P dashed. Because of this was just a reflection, the R value would have remained the same, but what happens to my x and y value when you reflect over the line y is equal to x? Okay, now this was a concept that we learnt in grade 9, and this is one of the reasons why we do transformations in grade 9. So I've written here in my bubble, when we reflect over y equals x, and I'm not too sure if you remember what the rule is. The rule is that any point, which is the point xy, will become the point yx. So basically our x and y coordinates literally swap around when you reflect over the line y equals x. So this means if I started with a point which was AB, the moment I reflect over the line y equals x, they don't stay the same, they actually swap. So what was AB becomes BA. Now hopefully you can start to see that that's why this type of reduction is going to be very different. In all the other reductions, when we folded over, for example, when we folded over the y-axis, so we could do 180 minus theta, nothing happened to the point except they changed sign, for example. So A and B never swapped. They were always exactly the same values, but their signs changed. And that's why we had what I called the four cousins, where nothing changed, just the signs. Now I'm going to erase that because that's not what's happening here. What's happening here is that something big is happening. My entire coordinate is swapping round. So now what we can do is we can monitor what is the sine of 90 minus theta, this new angle that I've created. What's the cos ratio and what's the tan ratio? So let's look at those three ratios. Let's look at sine of 90 minus theta. Now don't forget where 90 minus theta is. 90 minus theta is now this entire angle there. Now the definition of sine is the y value, which now at this new point is a, divided by the r, which is r. So instead of being b over r, which was sine of theta, sine of 90 minus theta isn't the same thing at all. In fact, it's a over r. If I look at cos, the definition of cos is the x value, which is actually now b, over r. So again, it's not the same as cos of theta. In fact, it's very different. So we're not getting the same effect that we got with the 180 minus. And if I look at tan of 90 plus theta, tan by definition is the y value, which in this case is a, over the x value, which is b. So again, tan of theta is not the same as tan of 90 plus theta. These are now entirely different. So what we noticed when we worked from 180 and 360 is that they were exactly the same, which is just a different sign. And eventually what we realized is the sign depended on what quadrant it is in. So as long as you can figure out the quadrant, we could just reduce it down to a ratio of theta and just say, okay, what is it, positive or negative based on the quadrant? Now we can't do that here because the letters are being jumbled up. But do we notice something? Do we notice that cos of 90 minus theta is not the same as cos theta? However, it is the same as sine theta. So cos of 90 minus theta actually reduces to sine theta. Now, why does that happen? That happens because our coordinates swapped around. And so the moment our coordinates swapped around, here b was representing the x value, and here b was representing the y value. Now that makes sense because our coordinates swapped. So the x value for 90 minus theta is actually the same as the y value for theta. And so that's why our names swapped. So the first thing that I've noticed so far is if I'm doing the cos of this angle of 90 minus theta, it doesn't reduce to cos theta, it reduces to sine theta. So my name swaps. Now the other thing I notice, if I look at sine, so sine of 90 minus theta is a over r, and that's not the same as sine theta, but it is the same as cos theta. So again, my name swaps. So I'll notice that sine of 90 degrees minus theta actually reduces to cos theta, not to sine theta, simply because what was my y value, which was a for 90 minus theta, is actually the same as my x value for theta, because my coordinates swapped when I did this reflection. Now what's pretty cool here is that you can finally understand the names of sine and cos. So actually sine's full name is sine, which is S-I-N-E, and cos's full name is cosine. I mean, we call it cos, but I don't know if you remember that cos is technically, its full name is cosine. Now, the reason why the one's called cosine and the other one's called sine is we call these co-ratios. Now, co-ratios are exactly this. The cos of 90 minus theta reduces to what we call its co-ratio. It's like its partner in this. So sine and cos are co-ratios when you do reduction from 90 degrees. Now I just want to pause and have a look at tan of 90 plus theta. So tan of 90 plus theta is a over b, and tan of theta is b over a. So there's kind of a relationship in that the one is the other guy flipped, which makes complete sense. Now we no longer study the other ratios, which are called sec, cosec, and cot. But actually tan has its relationship with its co-ratio, which is actually called cot. So tan actually stands for tangent, and cot stands for cotangent. So tan actually is a co-ratio with its partner called cotan. But we don't study that anymore. So we actually only have to worry about sine and cos. So in actual fact, we're never going to ask you tan of 90 plus an angle, because, well, I say that there's ways to get around if I ask you that, because that's not something we study. So the thing we need to focus on, I'm going to not erase that because I think it's important to see, but we need to focus on sine and cosine and their relationship. Now I want to go back up here because there's another angle. We've discussed 90 minus theta and we've seen how the name swaps. But now we have to look at 90 plus theta. So now the question is, how would I create an angle of 90 plus theta? Well, if I took P dashed and I reflected it over the y-axis, I would get a point which I would now call maybe P dash dashed. And this would be an angle of theta there. So that would be theta. So basically I would have taken P dashed and reflected over the y-axis. Now we know how to reflect over the y-axis. Basically your y value stays the same, so this would still say A, but your x value would change sign. So this would now be negative B. So notice it is still the swapped around version of your original P. And now I've added in the complexity that I've changed the sign of the x value. So now we can look at sine, cos, and tan of these 90 plus theta, this angle. Let me show you where that angle is. That angle of 90 plus theta is 90 plus theta. So this angle here that I've now drawn in blue is 90 degrees plus theta. So let's look at the ratios of that angle. So if I look at sine of 90 plus theta, by definition sine is y over r, which in this case is a over r. Cos by definition is x over r. Now this x value is now negative b, so negative b over r. And finally the definition of tan is y over x. So this is a over negative b, which I could just write as negative a over b. Now we also now want to compare, how does this compare to my original theta? So what we'll notice is that sine of 90 plus theta is a over r, which if I look at how that relates to theta, that's the same as cos of theta. So again, the moment I'm working from 90 degrees, what is a sine ratio is swapping to be the same as cos of theta. Now notice there's actually not even a sign difference because both of these are a over r. If I look at cos of 90 plus theta, 90 plus theta is negative b over r. So it's almost exactly the same as sine of theta. So the name is swapping. A cos ratio of 90 plus theta is swapping to be the same as sine theta, except notice there's now a negative sign. Now why is there a negative sign? Why isn't it the same thing as just sine theta? Well, you're working with cos, and this angle is in quadrant 2. And we know that in quadrant 2, only sine is positive. So notice that sine of 90 plus theta was exactly the same as cos theta. It was a over r. There was no sign issues, as in positive and negative issues. The moment we get to cos, because we're talking about an angle in the second quadrant, yes, my name's swapped, but I'm now negative b over r and not the same as positive b over r. Now I'm not going to look at the tan because of what I've said before. This idea of co-ratios and working from 90 degrees is not something we study in tan anymore. So basically we just need to go and summarize now, what have we noticed about sine and cos and working from 90 degrees? So let me make a summary. So hopefully what we've noticed is that this actually boils down to a very simple concept. Sine of 90 degrees minus theta does not reduce to sine theta like it did with the 180s. It actually reduces to cos of theta, simply because when I created this angle of 90 minus theta, the reflection that I did swapped x and y around, and so I swapped the name from sine to cos. exactly the same with sine of 90 plus theta. This will reduce to cos theta. Now notice there's no negative signs here to worry about because this is quadrant 2. And in quadrant 2, sine is positive. This is quadrant 1. If you were working with an angle which is 90 minus, you would be in quadrant 1. And so both of those are positive because sine is positive in quadrant 1 and 2. Right, so let's look at cos. Cos of 90 minus theta will not reduce to cos. Because of the reflection, the name will swap and this will reduce to sine theta. It will reduce to positive sine theta because this angle will be in quadrant 1 and cos is positive in quadrant 1. However, with cos of 90 plus theta, any angle of 90 plus is considered to be in quadrant 2 and cos is less than 0. So cos of an angle is less than 0 in quadrant 2. So this will reduce to the negative version of sine theta. Now this seems obviously a lot more complicated than the 180 degrees, and I suppose it is a little bit because your names are swapping. But notice this only occurs at 90 degrees, and it only occurs when you're working from 90 because of the transformations needed in order to create these two angles we're speaking about. Now again, this might now seem to throw us a bit because now we have to think a little bit differently, but in the next video we're basically going to summarize all these reduction rules down to 2 very easy questions, and then you no longer have to remember all these different things. Every single reduction comes down to answering 2 easy questions. So hopefully in the next video we can start grappling with that summary. Okay, now before we get there, let's just practice a couple of examples. So this first one says, without a calculator, determine the values of. So the moment I see sine 135, remember my thought is, can I rewrite 135 degrees? Now, when we have been choosing to rewrite 135 in the past, we have said, right, that is closest to 180, so we're going to do 180 minus an angle. However, now that we've done reduction using 90, we could change 135 to 90 plus an angle. So I'm going to show you both of these. So sine 135, we could rewrite 135 as 180 degrees minus 45. So you've set up your reduction. 180 minus 45 is 135. So I haven't changed the question. Okay, now I didn't have to do that. I could have said, or let me rewrite 135 as 90 plus 45. That also simplifies to 135. Okay, now let's do reduction of the first one. 180 minus 45 would be quadrant 2, so sine is positive, and when you're working from 180, your name stays the same, nothing changes. So I get sine of 45, which is root 2 over 2. Now, the other side is you'd say, oh gosh, look, I'm working from 90. Now 90 plus 45, 90 plus would be working in quadrant 2, so sine is positive, but my name will now change. We've learned that when we work from 90, your ratio name swaps to what we call its co-ratio. So what was sine now becomes cos. So this simplifies down to cos 45. Now notice I decided the sign of this. I decided whether this was positive or negative based on my original ratio, not on the fact that my name's changed. So always decide your sign first. Now cos of 45 is also root 2 over 2. So either way I got the same answer. So these are called co-ratios. Sine 45 and cos 45, those are co-ratios, and it's simply because 45 and 45 together make 90. Now which way would I choose to do this? Personally, I never ever ever choose to use 90 degrees unless I have to, because it results in the name change, and then if I mess that up, I've made a mistake. So I always choose 180 if I can. Okay, so let's just try a couple more. How could you rewrite 150? Well, first of all, you could write 150 as 180 degrees minus 30. That would simplify to 150. That would then reduce to, well, cos, this is in quadrant 2, and in quadrant 2, cos is negative. So cos would be negative in quadrant 2, and this would reduce to cos of 30 degrees. Because I'm working with 180, so my name does not swap. So negative cos 30 would be negative root 3 over 2. Now that's not the only way to do it. I could have rewritten 150 degrees as 90 degrees plus 60. Now this is still in quadrant 2. And cos in quadrant 2 means this will reduce to a negative. However, because we're working from 90 degrees, my ratio will swap to its co-ratio, which is sine. So I get negative sine of 60, which is also negative root 3 over 2. So notice our co-ratios are cos of 30 is called a co-ratio with sine of 60, because 60 and 30 make 90. So there's my connection. So questions like to exploit this idea of co-ratios. The moment I look at this, once I'm well practiced in trig, I would look at this question and say, well, the answer is 1. Because notice that 50 and 40 add together to give you 90. So there's definitely going to be a relationship here. Now, you don't want to rewrite both of them, so I want to keep one of them the same. So let's keep our bottom as sine 40. So let us try and rewrite 50, but using 40. So I would change 50 to 90 degrees minus 40. Now that's how you spot it. If two angles add together to give you 90, it means that you can work with the 90 in terms of co-ratios. Now 90 minus 40 is quadrant 1, so this will be positive, but the ratio of cos will change to sine. So when I reduce this, this changes to sine of 40 over sine of 40, which is 1. So this is a very common use for co-ratios. Always look out for when two angles can add together to give you 90, because then you can do reduction on one of them and change their name. So notice that we rewrote 50 degrees as 90 minus 40. Right, so let's just look at one last example. This example has 4 factors, so cos 180 minus theta. 180 minus theta would be quadrant 2, so cos would be negative, and my name is not changing because I'm working from 180. So that's negative cos theta. If I look at my next one, cos of 90 minus theta, 90 minus would be quadrant 1. However, so that makes this positive, because all ratios are positive in quadrant 1. However, cos will change to its co-ratio of sine, simply because I was working from 90 degrees, and so my name swaps. On to my next factor, 90 plus theta. 90 plus will be quadrant 2. Sine is positive. However, because I'm working from 90, my ratio will change to the co-ratio, which is cos. And finally, 180 plus theta is actually quadrant 3, and so sine is negative in quadrant 3, but my name will not change because I'm working from 180 degrees. So I get negative sine theta. And then to finally simplify that, well, I've got a negative divided by negative, so that will cancel. And I've got cos of a cos and sine of a sine. So basically all of them cancel, and this boils down to 1. Okay, the next video is going to summarize the whole of reduction down into 2 simple, easy questions. And then hopefully reduction is going to be something that you learn to love.